Okay, so last week we spent some time talking about the historical precedents of Noam Chomsky's theories and the historical development of the generative linguistic program. And today I want to talk specifically about the argument from the poverty of the stimulus. So, one of the ideas that Noam Chomsky has developed and has been pursued extensively in child language acquisition is the poverty of the stimulus argument. This idea is that the amount of information that's available to the child is not enough information in order to explain how children learn their language. This has been a very controversial idea and has engendered a number of rebuttals and lots of debate, which the Lisa Pearl article that I assigned for this week will describe in some detail and go into some careful discussion of. But I think the idea, although it's controversial, it shouldn't be. I think the idea itself is actually fairly innocuous because one of the things that we have learned about learning is that there has to be some kind of prior biases or some constraints or some material that's already in place in order for learning to happen in the first place. Anyway, so that's what I would like to talk about today. Exactly what is this poverty of the stimulus argument? How do we think about it? And what can we say about child language acquisition that's related to this bigger picture of understanding language and cognition? So I want to start by reminding ourselves what we mean by universal grammar and why there's so much attention on child language acquisition in the first place. So as we said last week, this idea that child language acquisition is the really important thing, it's kind of the central piece of generative linguistics, that is truly a novel contribution, right? So throughout the linguistics intellectual tradition, there has not been so much attention paid to how children do things until the work of Noam Chomsky. And this argument has really two parts to it, right? So the first part is the observation that children learn languages. So there's three words here, children learn languages, and all three of these words are important. So the first word here is children, right? So what we're trying to give an account of is why children, that is, young humans, are capable of learning languages, but we don't observe any other mammals or even other primates for that matter approximating this kind of behavior, right? We don't observe that even our closest primate relatives are capable of learning human language, at least in the way that we would recognize as linguists. And the second part is the word learn. So we observe that children do in fact learn something. One of the ways in which the universal grammar hypothesis is often mischaracterized is by suggesting that Chomsky's theory implies that children are born knowing some language innately. That is not the case, right? We are not innately born knowing English or Japanese or Wolof or whatever it is. Rather, the language that we learn is the language of our environment that we engage with through exposure over the first 3 to 5 years of life. And the last part is that children learn languages. So in order to have some theory of how children learn languages, we gotta know what language is, right? We have to have some theory of what language looks like. We have to have some understanding of that target state that the child has to approximate or that the child is trying to get to, in a sense. In other words, in order to explain how children learn languages, we have to have some theory of what they're learning. And I think this is something that is often underappreciated. If you go and read a lot of this research in theoretical linguistics and in child language acquisition, you see that there is actually a very tight connection, and many child language acquisitionists pay very close attention to what's happening in theoretical linguistics for that reason. Right, so in other words, children learn to transmute some kind of phonetic sequence if they are listening, or some kind of orthographic or sign signal if they are reading, or if they are perceiving a sign language, into some kind of grammatical representation that has some kind of semantics, right? So that is the kind of system that we're describing here. And the second observation that was not originally Noam Chomsky's idea, but again was really refined and repopularized and made to be central to the program, is that languages have many features in common, right? So as we said before, the original use of the term universal grammar predates Chomsky. It comes before Chomsky. And similarly, the idea that there's probably a good reason why the tools we use for describing one language work pretty well for other languages, right? That is, there's some kind of universal core, or there's some kind of basic blueprint from which languages are cut. So there are going to be differences. So here I have a Hindi sentence that means the same thing as the English sentence. And if you spend a couple of minutes looking, you'll see that there's some differences. Hindi puts the verb at the end. Hindi has, for instance, an aspirated ch sound and an unaspirated ch sound. And we could go further into detail, of course, but by and large, we see that languages have many features in common, right? They all involve some kind of syntactic structure. They often involve categories like nouns and verbs. They often have vowels and consonants. The predicational structures of language are very similar, etc., right? So what Chomsky's proposal is that we can unify these, right? We can probably say that these two observations are not independent, that the reason why languages have many features in common and the reason why children are capable of learning languages is the same reason, right? Namely, that blueprint, that set of commonalities that languages have are in some sense built into the child, right? When we are born as human babies with human brains, we already have some idea of how language is supposed to work, which radically simplifies the process of learning languages and also explains why even the smartest primate isn't capable of doing this, right? So if our primate cousins are not born with that blueprint, then that explains why a human child is capable of learning language in a way that our primate cousins aren't. So that's kind of the idea. Sometimes you'll see Chomsky give some kind of notation like this, which essentially says that what the learner does is it combines some experience, in this case of Hindi, with the initial state, right? So that means whatever stuff that child is born with. That might include things like specific knowledge about how language works, meaning specific details of nouns and verbs and syntactic structure and so on. But it's also going to include some things like memory and attention and reasoning skills, right? So basic cognitive skills that can underlie both language learning, but also the use of language and so on. And if we combine those two things together, presto, we get the language of that community. In this case, we would get some grammar of Hindi, right? So that's the basic idea. Now, obviously, if you go and study child language acquisition, you learn that things are a little bit more complicated than that. The process is obviously not instantaneous, but nonetheless, the basic idea still stands. So if we want to say anything about how we learn language, we have to think about how we learn anything, right? So what is learning and how could that possibly happen? So learning is surprisingly a difficult thing to study. It's hard to learn things about learning. But there's an essentially a largely, I guess I could say, consensus way of talking about learning that we observe in cognitive science, right? And especially when it comes to how children learn things. So how do we learn anything, right? So the basic idea is that learning is going from a state where you don't have knowledge to a state where you do have knowledge after being exposed to some data that's informative, right? So let's think through some of the variables here. So the first variable that's important is what in child language acquisition we call the input, right? So the input means whatever information is swirling around in the environment. There's a lot of information in the environment, right? So there are things that we might be referring to, there are words and sentences, and there's kind of social relations that are relevant, right? Children might be more interested in things that their parents say, and what their parents say might be informative to the child, so on and so forth. So the input is just whatever information a child could, in principle, think about. So if we were to apply this to simple cases like word learning, we could imagine a situation in which a child sees a frog and the child's parent says something like, "That is green." Yeah? So that is input, right? There's some environment that the child is in where there's a green frog, and that environment also contains the word green. So that is the trigger, that's the stimulus, the impetus for the child to learn something about the word green. Next, we consider the intake. So the distinction between the input and the intake is a subtle one, and it's one that's not often made. But this distinction is really elaborated on by work by Akira Omaki and Jeff Lidz, who are child language acquisitionists who talk about this distinction quite a bit. The intake is essentially the amount of information that actually gets to the child. And so this is an important distinction because we know that children don't necessarily attend to all of the information in their environment at all times, right? Children are, well, first of all, they sleep a lot. Second of all, when they're awake, they're playing, or maybe they're not necessarily listening to their parents or to their family members, right? So we know for one thing that just what information the child is attending to is a subset of the information that's available. And we also know that children have to process that information, right? There are some kind of psycholinguistic processes that must be launched in order to process the stimulus. And there's also visual stimulus processing, acoustic processing, etc., that children have to develop, right? So in order for children to use information about their environment, they have to have the precedent skills or cognitive capacities in order to access that information. So just to give a very obvious example, in the situation I described where there is a green frog in the visual space, and then the parent said that is green orally, meaning using their voice, a child who is deaf, for instance, might not have access to that acoustic signal, right? They would maybe see the frog, but they wouldn't hear the word green. And similarly, a child who is blind might be able to hear the word green if they have normal hearing, but would not see the green frog and then wouldn't have access to that part of that stimulus, right? I say this for two reasons. The first is just to demonstrate, right, that it's important to make the distinction between input and intake, because information that's in the environment may not necessarily be the kind of information that the child has access to. And I also say that because it's worth acknowledging that we know that children who are born blind or children who are born deaf are actually capable of learning language at essentially the same rate and with the same fidelity, and with the same success as their colleagues who have typical hearing and seeing capacity. So that means, right, that the amount of information that a child needs in order to learn language is not really it's really a subset of the information that's available to them, right? So here what I'm trying to imply is that if a child hears that is green, right, they're going to have access to the phonemes that they've been exposed to. They're going to have information about, say, the shape of the frog. Maybe they'll have information, maybe they'll notice information about the color of the frog. But there might be other aspects of the environment that they might not be attending to, right? So for instance, if a child hears that is green, they might not notice, for example, how many legs the frog has, right? They might notice the color, they might notice the shape, they might notice the phonemes, but they might not remember that frogs have 4 legs, let's say. Obviously, we know as adults that the word green only refers to the color, but the child doesn't know that yet. That's the problem that the child is trying to solve, so they have to pay attention to lots of properties, and if they happen to not pay attention to the color, then they're going to learn something incorrect about the word green. On that note, one of the things we also need to specify in our theory of how children learn things is the hypothesis space. And so this is where there's controversy, right? This is where things start becoming more complex. How do we learn things, right? So we know that there's some data that we have to process and we have to notice, but then what, right? So the basic view, I think, that we have articulated in theories of how learning works is that there has to be some way of either formulating hypotheses or there has to be some kinds of prior hypotheses that are already available to the child, right? So if you hear something like that is green, we might posit that green has something to do with the color, which again we know as adults is the right answer. And in which case we have to start considering all of the different possible colors that the word green could refer to, right? It might refer just to what we know to be the meaning of the word green, which is that color in between the blues and the yellows, but it might mean something like blue and green, it might be something like purple, blue and green, or it might mean something like green and yellow, or green, yellow, and orange. And I say this because we know that in the world's languages, that is the case. We do see, for instance, that the Japanese word aoi uh, ranges between what English speakers would call blue and green. So this is not an unusual or ridiculous hypothesis to consider. This is actually a hypothesis that a child apparently needs to distinguish between, right? The child might also consider the hypothesis that the word green refers to the shape of the frog. They might consider that it means the two eyes, right? The child might consider that the meaning of the word green means has four legs, or any number of properties that might be attributed to the frog, right? That it's alive, that it can move, that it's an animal, that it means frog, right? It means the kind of animal that we're observing. The hypothesis space is quite large, right? And what information the child must have already had access to prior to encountering the word in this environment is where there's going to be some pretty big controversy. The other place where there's going to be some controversy is then we have to say something about the learning algorithm, right? So this again is this is a bit of a subtle point, but we have to say something about how the child starts to adjudicate between these hypotheses. Now that they've experienced this experience, right, hearing that word in the environment where there's a green frog, then what? What does the child do? They have to somehow use that information to either update or reject or accept or manipulate or formulate those hypotheses, right? So we might imagine, right, that if a child hears that is green, they might reject the hypothesis that the word green means something like green or red. They might, for whatever reason, reject the idea that green means alive or refers to the shape of the frog, etc., etc. And so the way that children navigate and adjust the hypothesis space, right, that learning algorithm, is where there's again lots and lots of controversy. So I want to say, right, these kinds of problems are not unique to language, obviously. Learning anything has this full range of problems, right? There has to be some information that's available to the learner, either a child who's learning language or an adult who's learning linguistics or what have you. There has to be some way for them to incorporate that information or process that information, and then they have to add that to some space of knowledge that they already have prior. And then they have to update their prior beliefs or their hypotheses accordingly. So I say that because to say that this is sometimes called in philosophy a problem of induction. The problem of induction is very, very, very old. So you may have heard of the word induction before, you may not have. In philosophy and in logic, we make a distinction between deduction and induction. A deduction is a inference that's made that's guaranteed to be true, right? So if I say something like, John is a tall person, right? Then that implies necessarily that John is a person, right? There's no way for the first sentence to be true and for the second sentence to be false. If you go and study formal logic, that's what you study. You study how deduction works. Induction, however, is what we're talking about here. Induction is our ability to infer what's going to happen in the future given our past experience. So David Hume, who's a philosopher, posited, right, that we can never know for sure the answer to the question, will the sun rise tomorrow? Now, 99.9999% of the time in the past, the sun has risen, right? I don't think I've lived a day where there wasn't a sunrise, yeah? Even on, I spent a lot of my life in South Dakota and Minnesota. There was a sunrise. It might have been at, 11 a.m., but sunrises occurred. And I'm pretty darn sure that tomorrow there will be a sunrise also, but I can't guarantee that. I can't know that for certain, right? It might be the case that, the sun explodes tomorrow. Surely someday there will not be a sunrise. There won't be an Earth, or there won't be a sun, or there won't be either, right, after the heat death of the universe. But so there's no guarantee with full confidence that there will be a sunrise tomorrow. Nonetheless, we kind of live our lives with the assumption that there will be a sunrise, right? We're pretty darn confident that there will be one. And that's what we're talking about here, right? We're talking about inferring something that is not guaranteed from the input. There's two other examples that I think are worth knowing for a linguist. Both of these are posited in by philosophers, and they're posited for slightly different reasons, but those reasons are maybe not super important for our purposes today. So the philosopher and logician W.V. Quine posited an example that's called the Gavagai example. This is a very cute example. W.V. Quine asks us to imagine that we are visiting some location that we've never been to before, that has a different culture than ours, and that has a different language than ours. And we're walking around, and then a rabbit jumps from nowhere, and someone shouts, Gavagai. Now, what does Gavagai mean? Well, we might infer, right? We might induce that Gavagai might mean something like rabbit, right? But it doesn't have to mean that. Gavagai could mean something like watch out, right? Or it could mean something like hooray, right? If the person who saw it really likes rabbits. It could also mean really bizarre things that we probably would not say. But again, there's no guarantee that this person isn't trying to say this. It could mean something like furry thing, right? It could mean something like what W.V. Quine suggested, undetached rabbit parts, right? It could mean a rabbit's foot and a rabbit's ear and a rabbit's head, etc., that happen to be connected in some capacity or in some way, without it necessarily meaning like a living creature that's an animal, that's a rabbit. Or it could also mean something like rabbitness or rabbithood, right? It could refer to kind of the abstract property of being a rabbit without necessarily meaning the animal itself. Now, so those last ones are kind of bizarre and kind of funny and kind of ridiculous, but that's the point in a sense, right? The point in a sense is that we feel like it probably means the animal, right? But the logical set of possibilities is quite literally infinite, right? There's an infinite number of possibilities for what Gavagai could mean, but some of them are more plausible than others. Just a side note, what Quine was actually trying to say with this example is something that is kind of a subtle point. What W.V. Quine was trying to say was that translation is in principle not truly possible. What Quine wanted to say is that Gavagai here is a word that's uttered in a context, and the only way we can really understand what Gavagai could mean is to see Gavagai used in all other contexts that word could be used in. And because the word Gavagai does not have exactly the same context that the word rabbit has, namely, this person did not say rabbit, he said Gavagai, right? That's a context which Gavagai is used, but rabbit is not used. That means Gavagai does not mean the same thing as rabbit. I actually don't know if I agree with that point. His point, I think, is interesting. It's worth thinking about. But for our purposes, what merits discussion here, right, is this idea that there's a very large range of meanings that are possible here. Context can help guide those interpretations, but a single context never fully specifies it. A somewhat related example is an argument by Nelson Goodman, which he calls the new riddle of induction. Again, the details of which are interesting, and I think linguists, especially those who have more interest in philosophy and semantics, should think about this or should learn about this. But for our purposes, again, just demonstrates that there's a very kind of a literal infinite number of possible interpretations or possible hypotheses we can consider for a word meaning, many of which seem ludicrous to us, but that's again the point. Why are they ludicrous? How do we know that? What prior biases do we have that bear on this issue? So Nelson Goodman asks us to consider that the word green does not mean what we think it means as native speakers of English who are adults who know what the word green means. Nelson Goodman asks us to consider that green means something like the word grew. So grew means that something is green before the year 2475 or some arbitrary future date, but then means blue or red or orange after the year 2475. How would we know? How would we know that green means green and doesn't mean grew? How do we know it means green today but after that future date means a totally different color, right? How do we know that that's not what the word means? That's hard to know, right? There's really no way you could tell. There's no way you could, as humans who are alive in the year 2025, tell that the word green means what it actually means the first shade that I have here on the slide, and not the first shade today, but then the second shade at another time. Um, Again, so what Nelson Goodman's argument really is about here is how we can tell what concepts are and what word meanings could be if they are variable, or if they can change, or if they're not quote unquote law-like, right? If they're not meant to be kind of eternal consistent descriptions of things that can be subject to being tested, right? Something that shifts meaning at some arbitrary future date is not something that we can really verify. Anyway, I like these examples. Linguists and semanticists and philosophers of language really like these examples for different reasons. For our purposes, it really demonstrates that the set of hypotheses that a learner has access to are, in principle, very difficult to distinguish between, right? So that's what I'm talking about when we talk about induction, right? A lot of what we're discussing today is induction, meaning how do we make a guess about what a word could mean, or what a syntactic structure could be, or what the phonemes of my language could be, given the data that I have access to. We have to have some biases, right? We have to have some hypotheses already available to us, and we have to know how to compare those hypotheses against each other, and we probably have to have some prior biases about what's possible and what's feasible, and what isn't possible. That's universal grammar, right? Universal grammar is, here are my sets of hypotheses about how language probably works. Here are some guesses about how language probably doesn't work. And here are some ways for using information in my environment to update and to narrow in on those hypotheses. So I also want to spend a little bit of time talking about what learning algorithms are. As I've said before, one of the things that we need to specify is the learning algorithm. So the Pearl paper goes a little bit into this, but not a whole lot. So I want to spend a little bit of time thinking about how we can think about this. There are lots of learning algorithms in child language acquisition and in cognitive science in child development, generally speaking. There's lots of ways in which learning could happen, right? I want to just mention a few. One that you may have heard of, and that I think is a very powerful tool, and that's very popular in child language acquisition and many other domains of studying how learning works, is Bayes' theorem. Bayes' theorem can be very complex, and the way that it gets used can be very complex, but the idea is actually pretty simple. Bayes' theorem is often expressed with this equation, which says that the posterior, which is the probability that some hypothesis is right given some data that I'm observing, is proportional to the likelihood times the prior. So the likelihood is the probability of the data given the hypothesis, and the prior is the probability of the hypothesis itself. So that might not really make sense to you, but the basic idea is, when we want to come up with a good explanation for some data, we have to think about how good that explanation explains the data. Is it a good explanation for the data? And then we also ask ourselves, how plausible do we think that data is before we even think about how plausible is that hypothesis before we even think about the data, right? So in other words, there might be some hypotheses that are very, very, very likely, but maybe they're not a great fit for the data, but that probably means we should still consider it. We should still kind of think about it as a possibility. Similarly, there might be some hypotheses that are very unlikely or that are very bizarre, but if they explain the data really well, then maybe we should consider those as well, right? So in other words, it's a balancing act between the reasonableness of the hypothesis, right? The reasonableness of the explanation, and how good that explanation actually accounts for the data that we're observing. So this is an example that I don't know, I probably stole this from someone, but I use this a lot. So imagine I come home from work one day and I see that my TV screen is broken, right? It's completely shattered. Now, at this point, I could formulate, again, an infinite number of hypotheses. This is a screen recording, so I'm not going to give you an infinite number of hypotheses. I'll give you three. One hypothesis is that my cats were being rowdy, right? They were running around, attacking stuff, throwing their mouse around the house, right, and making a bit of a mess, and that maybe resulted in the TV being broken. Another hypothesis that I might consider is that there was a rainstorm, right? It got rainy outside. A third hypothesis is that there were some aliens that came from space who really hate TVs, and they happened to land right in my apartment. They saw my TV, they shot their laser gun and destroyed it, and then cleaned up all the mess and then left, leaving no trace except for the broken TV. Now, you probably notice, right, that these hypotheses are not equal, right? So the hypothesis that my cats were being rowdy, maybe we say that explains the data 50%, right? So when my cats play and make a mess, sometimes they knock stuff over, but sometimes they don't, right? So it's not a great explanation for the data, but it's not a bad explanation either. So it's kind of a middle of the road explanation of the data. So the likelihood I estimated at 50%. But the prior is very high, meaning that it's very likely, without even thinking about the TV being broken or not, it's very likely that my cats are being rowdy. They're rowdy all the time, actually. So that's actually a very high prior, right? The second hypothesis, there was a rainstorm, that's a terrible explanation for the data, right? There being a rainstorm has nothing to do with my TV becoming broken. Now, it's not impossible, right? It could be that there was a rainstorm and then there was a flood, or, there was lightning that struck and it happened to strike exactly through my window in a way that broke my TV. That's probably a bad explanation, though, right? That's probably is not a very good explanation of the data that I'm observing. And right, it's probably not also a very likely explanation, meaning that the prior probability, meaning the likelihood that hypothesis is the case, is probably not very high either. Now, rainstorms aren't unusual, right? But they don't happen every single day. So if I come home, my first guess isn't going to be there was a rainstorm today. Lastly, that third hypothesis, the TV hating aliens invaded my apartment, that explains the data almost perfectly, right? I mean, that's a very good explanation. It captures the data with a very high probability, but it's extremely unlikely, right? The probability that there are such things as TV hating aliens is probably very, 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 very low. So the idea behind Bayes' theorem is we kind of multiply these things together to get some estimate of how likely the hypothesis is given the data. And we see that if I do some math here with these numbers that I estimated, we see that hypothesis 1 wins, right? Now, I went through all of this just to say that you will probably see Bayes' theorem being used in lots of different contexts, and it's very powerful. And if you haven't been exposed to this, then I wanted you to see what it can be used for. The reason why Bayes' theorem is difficult or complicated to use is, where do these numbers come from, right? So we have to do some estimation, and that process is complex and it's not naive, right? I just made up these numbers, but obviously if we want to use this in a scientific way, we're not just making up numbers randomly. We have to derive them somehow, or we have to create usually some kind of distribution that gives a range of possibilities, and that's when things start becoming kind of complicated. And the other issue with these kinds of Bayesian, with these kind of Bayesian approaches, is they often require a lot of data to work. And it might not be that children have access to a lot of data all of the time, depending on what they're trying to learn. Another possibility that was explored in the paper, and I think you may have intuited, or you may have learned about as Occam's razor, is something called minimum description length. Minimum description length is a very popular idea, actually in Noam Chomsky's earliest work, and he actually posited that this might be the way that children learn grammars, posits that we select hypotheses that explain the data that are the most simple in terms of their description. In other words, this could handle the GRU case pretty easily, right? So if we're considering one hypothesis that says X is that shade of color, and hypothesis 2 said it's that shade of color before the year 2475, but then the other shade after, well, that first statement is just simpler when we spell it out. Now, part of the problem with using MDL, or minimum description length, is you have to get those descriptions somehow, right? So in order for that to work, you already have to have some vocabulary or some language to state what those hypotheses could be, right? But this is another idea that I think is a very powerful one to consider. Lastly, I want to just mention an actual finding that we have from child language acquisition, which is called fast mapping. Fast mapping is a hypothesized procedure or precise algorithm which says that when a child is exposed to some new linguistic stimulus and they're not sure how to interpret, they just kind of take a stab at it, right? So if you're a child and you hear, "Oh, look, a Zud," and you see a picture of a door and a picture of a bear, well, hell, I don't know. I guess it's a bear, right? That's kind of the idea. So the child kind of commits full throttle with full commitment to the idea that Zud means bear, and then in another context, they can then reconsider that hypothesis if they need to, right? So if you hear something like, "Oh, look, a Zud," well, hey, look, there's a bear. So that's further evidence that my idea was correct. But if the child thought that Zud meant door, and then they're in another context where they hear Zud and there's no door, that might be a trigger for them to reconsider their hypothesis. Now, I say this because, again, the poverty of the stimulus argument is that children don't have a lot of information, right? They don't actually get enough information to determine their language. Now, so we've already seen that when I say that children don't get enough information, that's because A, without any prior biases, without any prior hypotheses, without any algorithm for selecting between hypotheses, no amount of data is going to be good enough, right? There's no such thing as a way to learn without having some way of stating hypotheses and comparing hypotheses, evaluating it against the data, and some biases about how to navigate through those. And the second point is children do seem to be able to capitalize on the little information that they do have, right? So learning algorithms that require lots and lots and lots and lots of data might not be good models for how children do things. So I want to mention that part. How else might we study learning, right? So we said a little bit about learning algorithms. So how do we begin to start answering this question? How do we begin to start answering, what do children need to know in order to learn language, right? What do we have to posit is in universal grammar? What do we have to posit is their learning algorithm? How do they update hypotheses, etc.? So in child language acquisition, there's lots of ways we can do this. One way we can do research is we can do corpus studies. So I have a link here to Childus. Childus is a big repository of corpora of child-directed speech. So we have lots of transcriptions of parents and children interacting, of children interacting with other children, of parents speaking to each other and a child around. So these are ways of estimating what children might have access to. So again, the poverty of the stimulus argument says that the information children have access to does not determine the language that they have, but we would like to know what information children do in fact have access to, right? What kinds of syntactic structures, what kinds of words, what kinds of phonemes, etc. And again, one of the things that you can then go and explore is you can then go explore what information do children actually have access to. I can say as someone who has spent some time looking a lot at Childus, in my dissertation work, I spent a lot of time looking at Childus. It's pretty tedious. Parents don't really say a whole lot of interesting things to their children, in my opinion. That's my opinion. But so for the particular kinds of phenomena that I was interested in looking at in my PhD thesis, there basically just weren't anything. There wasn't anything in Childus. Childus was basically completely empty of the kind of phenomena that I was interested in, yet children seem to learn what I was interested in the first place. And I can talk more about that during class if you're curious to learn more about that. The second thing we can do that's fairly related is we can implement some of these models given some estimate of some data and then look to see what kinds of generalizations those models make, right? So by making formal computational models, we can see what kinds of generalizations are predicted given some learning algorithm or given some data. So here I have a plot from something we'll talk more about next week, which is the quote-unquote past tense debate, which concerns how children might learn the form of regular verbs like kicked and the form of irregular verbs like went, right? Not goed, but went. And the argument in this graph is that when a particular kind of learning model is exposed to a bunch of verbs, both in present and past tense, it basically gets the regular verbs right pretty quickly, but then it struggles with the irregular verbs. And more interestingly, it starts off getting the irregular verbs correct at first and then becomes bad and then slowly returns to baseline. We'll see that this is something that actual human children do, which is why this is an interesting thing to discuss, right? So what we're showing you here is how this model changes or adjusts as it accumulates more data over time. The other way we can study child language acquisition is by, the other way we can study how learning works is by doing child language acquisition experiments. I've already alluded to one. I already alluded to a particular example, which is this project, this paper by Truswell, Medina, Haffrey, and Gleitman, in which children were exposed to words in ambiguous contexts, and then we observed whether children thought that a word like zud meant bear or door. So child language acquisition experiments are useful for two purposes. First of all, they can show us what children actually know already, right? And what kinds of psycholinguistic processing they are capable of doing at different ages. And it also can be used to explore these different kinds of learning models, right? We can kind of create small model examples of learning, right? Like the example I have here, in which a child is exposed to a novel word, and then see what kinds of information they try out or what kinds of information they try to extract from it. So this is a way of kind of artificially creating environments where children might learn something, and then we can maybe get a sense of how they learn. Okay, so I just spent a good 20-ish minutes talking about child language acquisition as a field and how we explore learning and as a field in general. Now let's really get to kind of the meat of the argument. So I want to go through an example that Noam Chomsky uses a lot to illustrate his point. And this is the argument of structure dependence. Structure dependence is an interesting argument, I think, but I think people think that this particular example is more important than it actually is, right? This is an example. And as we talk about things like islands in a few weeks, we'll see a broader range of examples that are relevant here. But nonetheless, this is the example people always use, and for that reason, it's worth exploring. So let's look at an observation, right? In English, we can pair up a declarative sentence and an interrogative sentence. We can have the declarative sentence, the girl can run, and if we know that sentence and we know English, then we know the interrogative is can the girl run, and vice versa. So this is something that we have to learn, right? So if you learn a language like Hindi, this is not how you form a yes/no question. You do it differently in Hindi. If you learn Japanese or Mandarin Chinese, you put something at the end, right? If you speak a language like Spanish, you put the verb at the beginning, right? So different languages do slightly different things. Now, just as we saw before, the number of hypotheses here are, in principle, infinite. There's all kinds of ways we could think about how to relate these two sentences, right? We could formulate a rule that says something like, move the main auxiliary to the beginning of the sentence. Sorry about my cat. Okay, sorry about that. Where was I? Okay, right. So we can formulate a number of hypotheses about how to relate the declarative and the interrogative, right? So we know the actual answer is something like find the main auxiliary of the sentence and move that to the beginning of the sentence, right? But there's, as always, an infinite number of possibilities we could consider, some of which seem ridiculous to us if we know something about language, But again, that's what we're trying to solve for. We're trying to explain what we know about language. So another hypothesis we might consider is that the first auxiliary in the sentence, that is the first in the string, not necessarily the highest in the structure, gets moved to the beginning. Another hypothesis is take any auxiliary, doesn't really matter which one, and put that at the beginning of the sentence. Another possibility is if you see the word can in the sentence, move that, but if you don't have the word can, then you don't have to do anything. Another possibility is take any word and put it at the beginning of the sentence. It doesn't have to be an auxiliary. Maybe it's put the third word before the first word. Maybe it's move the main auxiliary, but it doesn't have to be the beginning of the sentence. It could just be anywhere, or it could be 2 words back, or etc., 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 etc. We could play this game for a literal eternity. Okay, so now imagine that we are lucky enough as a 5-year-old to be exposed to the pair of sentences, the girl who can run should swim, and the interrogative form, should the girl who can run swim. So these are both pretty difficult sentences to say, I would say, right? So these are both complex sentences. There's 2 auxiliaries. They're different auxiliaries, right? They have different kinds of modal forces. If you've taken semantics and know what that word means, these are kind of complicated sentences, right? But in the first sentence, we see that the first verb is the first auxiliary is the word can, which is inside of a subject relative clause, and then the main auxiliary is the word should. And then in the interrogative, it's the main auxiliary that has moved, whereas that first auxiliary can stays where it belongs, right? So if we are lucky enough to get exposed to this sentence, then we know that we can start ruling out a few hypotheses, right? So in other words, there's a few hypotheses that are listed here that are compatible with this data, and there are some hypotheses on this list that are incompatible with this data. So namely, hypothesis 1, the correct hypothesis, right, is compatible with both facts, right? Because in both sentences, the main auxiliary has been moved. In the first sentence, it's the only auxiliary, the word can. And in the second sentence, it's the main auxiliary should, and then that first auxiliary, which is inside of a relative clause, stays put. So if we are exposed to that sentence, right, we have one hypothesis that's now compatible with both data points, but now we have to rule out hypothesis 2, which is sensitive to the position in the sentence, the first auxiliary. And we can also rule out hypothesis 4, which says that the word can is the one that has to move, because that's not what we observed. And we can also now rule out a hypothesis 6, which says it's the third word, because in this case, the third word is the word who, and that did not move. So that's good. We've ruled out some hypotheses, but infinity minus 3 is still infinity. Keep that in mind. And we also have a hypothesis that's another hypothesis that's compatible with both, and will always be compatible with data that's compatible with hypothesis 1. And that's hypothesis 3, move some auxiliary to the beginning of the sentence. So this is where we would have to trust our learning algorithm. So in the Pearl paper, she will spend some time talking about indirect negative evidence. Indirect negative evidence is basically the idea that my hypothesis predicts some things should be happening that suspiciously aren't, right? And if that thing that I predict should happen at least occasionally never happens, in other words, it's very low probability, then that might mean I need to reevaluate my hypotheses so as to not expect it in the first place. That's a very tough game to play. It's actually very tough. That's tough to do, right? Because, as I said before, we know children can learn from a very small number of tokens, right? So we know that children are capable of learning some facts about their language after just a few observations. So having a learning algorithm that penalizes hypotheses that make predictions that are not frequently attested could be dangerous, right? It could actually get the child to learn something that is incorrect. Additionally, look at these sentences that I just talked through. The girl who can run should swim. When would we say, like, what would we say that, right? Do we really think that a 3-year-old has this A in their input and B in their intake? Do we think that a child is capable of processing, should the girl who can run swim, sufficiently enough to notice the structure of the sentence warrants hypothesis 1 but not hypothesis 2? That's the bet that we would have to take if we want to argue against the poverty of the stimulus argument, right? So here's what Chomsky says. There aren't infinite hypotheses, there's one. There's one hypothesis on the table, and that is children know that the rule of grammar, that the rules of grammar are formulated over the syntactic structure. So we don't have access to things like first or some auxiliary even, or even necessarily things like the word can or the third word, etc., etc., etc. Tons of hypotheses are knocked off of the table, and there's one left, which is something like I have to do something to main auxiliaries, right? If I'm noticing auxiliaries are moving around, I gotta do the main auxiliary if it's moving to the main clause edge. If you've taken classes in advanced syntax, then you probably know the answer is even more restricted than that. It's going to be something like I make questions by putting something in C, which is probably at the left edge of the sentence. And if it's not at the left edge, it's probably at the right edge of the sentence. And there's only a small number of things I can do. I can either move T, which can be an auxiliary if you're English, or a main verb if you're Spanish or French, into that position, or otherwise I just got to stick a morpheme into that position, right? So I mentioned languages like Hindi, that's essentially what they do. The word is kia, and you put the word kia in that C position. Or if you're Japanese and you have a word ka, which goes at the end of the sentence, right? So the space of hypotheses is actually pretty small. And again, notice what I did. I used evidence from other languages, right? The universal grammar hypothesis is that what children know is the stuff that's universal. And the stuff that's universal is the stuff that children know. So there's probably good reason why question formation looks so similar across languages, and that children seem to learn how question formation works. Or at least that's the argument. Now, of course, we might wonder, well, how often do children see these sentences like the girl who can run should swim, right? Maybe children actually are exposed to this sentence quite often. I questioned whether that information could get into the intake, right? Whether children should be able to process those sentences, but we can still look at the input. We can still look at what children are exposed to. And the answer is they probably don't see those structures very often. So Pullman, Schultz, and Leggett and Yang both have some kind of discussion about this, but it turns out these kinds of sentences aren't completely absent, but they're astonishingly rare, right? And if we want our theory to bank on the assumption that children are going to always learn something from very, very rare structures, that's maybe a dangerous game to play, right? That maybe is not the right hypothesis. So it turns out that if we're just paying attention to question formation, we don't really have a very good explanation of how children figure this stuff out in the first place, right? In the Pearl paper, she spent some time discussing other possibilities. So another possibility that's been being explored in the last 20 years is that maybe it's not necessarily about question formation per se, but maybe there's so many other pieces of evidence in the input that says I need to pay attention to syntactic structure, not linear order, and from that, they're able to bootstrap or infer that their rule for question formation has to also be defined over a syntactic structure. So the jury's still out, right? But notice that in order for even that to make sense, what I just described, children have to know what syntactic structure is. They have to have some way of formulating those hypotheses in the first place. Another thing you might be wondering at this point is, well, what do children actually know? Again, this is very relevant to the conversation, and it turns out that children know quite a lot. So even though children don't hear these very kind of complex question structures where you have two auxiliaries and the main auxiliary is moved over the first auxiliary, we can test whether children get the right answer anyway, right? So we can test whether children know already what auxiliary is the one to be moved by developing a child language acquisition experiment to test exactly that question. So this is a study by Crane and Nakayama that's cited in the Pearl paper. I'm sorry I didn't actually put it on the slide here, but if you go look at Crane and the Pearl paper, the citation is available there. The experiment is very cute. It involves asking 3, 4, and 5-year-olds to ask questions to a puppet of Jabba the Hutt. This is a study done in the mid-'80s, so Star Wars craze was in the air. And the way that the critical trials were conducted would be the experimenter would use an embedded clause that has a double H that's a double H an interrogative embedded clause, right? But it's embedded, so embedded clauses in English don't involve movement of an auxiliary. So we have sentences like ask Jabba if the dog that is sleeping is on the big blue bench. So in this sentence, we have two auxiliaries, two different ises, and the question is which is left in place. Oh, that's say that 10 times fast, right? So which auxiliary is moved by the child? Which of the two ises is moved? And it turns out that children pretty much get the answer right? So overwhelmingly, children get the answer right. The 4 and 5-year-olds pretty much always get the answer right. So that suggests that at least by age, by the late 4s, if you haven't seen this notation, 3:2, this is kind of child language developmentalist ease for 3 years and 2 months. So this says children ages 3 years and 2 months to 5 years and 11 months performed remarkably adult-like. So overwhelmingly, the population that they're testing here basically get the answer right. They always pick the main auxiliary to move, and they leave that first auxiliary in that relative clause that is sleeping alone. They leave it alone. But the other finding from this study is that when children make errors, when that younger population, the 3 year and 2 months to 4 year and 7 month population, make errors, the errors they make are not random, right? And they are not errors in which they move the wrong auxiliary. The most common error is one in which they put in an extra auxiliary at the left edge of the sentence. So they'll say things like, is the dog that is sleeping is on the big blue bench. Now, I want to leave this here because I want to discuss why should that be the case? Why might a child make that error, right? And what might that tell us about the nature of the hypothesis space that the child is exploring? So I'll leave that as a question for our discussion in class. But I think that this kind of error is also very telling. So just to conclude the discussion of the poverty to stimulus, the poverty to stimulus argument is a very simple argument, right? The poverty to stimulus argument is children learn languages, but other things don't. So children have to have something that lets them do that other species don't have, right? And we also think that the data that the child is exposed to is not sufficient for learning language, because no data is sufficient for learning anything unless you have some way of formulating hypotheses, navigating those hypotheses, and some learning algorithm that you can use, right? So I think the claim is that universal grammar is either some knowledge that we have about how language works, some conglomeration of skills and capacities and other kinds of representations that allow us to understand language ultimately, or both. Yeah. In the Pearl paper, she suggests that a lot of the disagreement is really just about whether universal grammar is grammar or not, right? Whether that knowledge that children are born with is about language or whether it's general to that. But I think it's a little, as I said before, it's almost a little puzzling to me that people question this idea of poverty to stimulus, right? Because again, poverty to stimulus is really just a generic property of learning in general. And they question the universal grammar idea, but again, I find that a bit bizarre because, in my opinion, I'm editorializing right now, everybody has to have something like a theory of universal grammar, They just might disagree about what goes in that box, right? People who follow the views of Chomsky might suppose that there is actually detailed grammatical information there, the kinds of stuff you learn in a linguistics class. Others might say that box is maybe not full of language stuff per se, but can get filled with language stuff, let's say. Okay, and at that, I will leave the conversation for now.